Okay, so why, what, and how? I wanted to get started quite quickly on this, but I do need to sort of give a little bit of a sort of introduction first. Really, JTAG is a child of the 80s, like most of the technology I think we see this evening. And it was originally conceived as mass electronics manufacturers started to sort of take off in the 80s. It became more and more difficult to test, and as you sort of surface mount technology started to be introduced, and chips with lots of pins, PGA and such things, it became more and more difficult to work out if the board didn't work, why it didn't work, and conversely, if it was going to work by the time it reached the customer. And so this action group, JTAG, was formed, and they came up with the standard IEEE 1149.1. So JTAG and that standard are sort of referred to sort of synonymously. So the first use case really they had for this was they wanted some way to do what they call boundary scan, which is effectively being able to control each of the pins on a device independently, so that you could check, are they shorted, are they soldered properly, but also beyond that you could actually use it for programming PLDs and such things. Again, if you connected to a microprocessor, you can potentially control all the address and data pins and clock data onto your bus as well. So it's quite powerful in terms of what they came up with. But initially it wasn't really used for debugging, which is what the software engineers we like to do. So by the late 90s, JTAG was starting to be used on processors to begin to either do similar things to ROM monitors or even ultimately to phase them out. So I first used JTAG in about 96 on a TI DSP, where it didn't have a ROM monitor. Your only way of programming and debugging the device was via JTAG. As a standard, JTAG was designed not to be, well, let's say CPU dependent, but it's really pretty much for any relatively complex chip that you have on the board. Some Ethernet PHYs have JTAG support. Often you'll see it on bus controllers, like again, things like VME or compact PCI bridges and so on. But the key thing here is, from a CPU perspective, when you start debugging, although the JTAG pins are largely CPU independent, there's a lot of software dependency to make your CPU do the right thing, to control it in detail. Beyond basic JTAG control, but effectively controlling the CPU, there are things like the Nexus extensions, which allow you to do real-time instruction and data trace, modify memory while the CPU is still executing, and such things as well. So beyond basic JTAG level, which I'm going to be talking mostly about today, there's lots of things which you can do. Often they require much more expensive, much more sophisticated interfaces to your target, and not all targets support them, but it's just sort of to know that they are where they are. So, at least in concept, again, there's a Wikipedia page there if you're interested, give that link a follow. But the idea is that you've got potentially multiple devices on your board, and you want to connect to them all with as few pins as possible. So the normal JTAG interface has 4 pins. The TMS, which is your mode select, this controls your state machine, which I'll come on to in a little bit. Then you've got your clock, a data in and a data out pin. So essentially it's a serial interface with a couple of sort of extra channels, or a synchronous serial interface. So you daisy chain the test data into the test data out on each device and back into your controller, and TMS and TCK are bussed across all your devices. in terms of a schematic view of things, this is off a real board, a PowerPC board from NXP, where the normal way that these are connected up is you can see here the 4 JTAG pins, TMS, TCK, TDI, and TDO, you mentioned before. Well, the input pins, TMS, TCK, and TDI, are all used with pull-up connectors, pull-up resistors rather. So again, being an 80s kind of design, they were using open collector outputs, so open collector inputs, which means when you're not driving the signal, it's pulled up to whatever your I/O voltage is, and when you do drive the signal, it drives to 0 on the bus or on the pin. So if you're trying to retrofit JTAG onto a board which doesn't have it, you may find that you need to add some pull-up resistors and such things. There's also an additional pin here, which I mentioned, which is kind of optional in the JTAG standard, your test reset pin. And this, as it says, it resets the JTAG tap controller, test access port controller on the device. And again, you'll often see this actually pulled low instead of pulled high to disable JTAG functionality because it's intended for test. So in a production board, you don't want it to be accidentally enabled. Again, that can cause you problems for sort of aftermarket devices if you're trying to retrofit a JTAG connection. So again, I've mostly put this state machine up because it shows you that you're not just going to connect a terminal up to your JTAG pins and issue some commands. This is a much, much lower level protocol. And as I say, with the state that you're in is controlled by your clock and your TMS signal. So on each edge of the clock, the TMS signal is sampled and you can move around the state machine. And it's designed so that 5 ones, no matter where you are in the state machine, will always take you back to the reset state. So whichever state you're in, it really doesn't matter. If you only clock 1s back in, you get back to reset somehow, one way or another. So this is why one of the reasons why the reset pin is optional. I guess the really important states are your shift IR state and your shift DR state. So when you've clocked your TMS into one of these states, then you start actually populating your shift register on your test access point, your controller hardware, to get the JTAG to do something. And ultimately, when it hits the update IR state, then it will action that. In fact, that's the message that this is now in the, we've got the entire contents in our register, whether it's the instruction register or the data register. So we want to do something. So again, we're going to need some software to control this. And, well, sorry, hardware to interface to it, rather. In the olden days, people used to use parallel ports and bit bang and whatever else, and it was pretty messy. These days, you'll get one of these nice little devices from your favorite Chinese vendor for about £10. So it plugs into your USB port, and on this one, it's got a little JTAG connector underneath. So again, this particular variant is designed for ARM devices in that it's got the Coresight 10 header, which you'll see on lots and lots of Cortex-M boards. Again, it's worth having, if you're buying a generic FTDI board, again, there'll be oodles on AliExpress or Banggood or wherever you are, it's worth making sure that it's one of the ones which supports the MPSSE hardware, the multi-protocol synchronous serial engine, which is needed for JTAG. If it's not, then it's just a serial port. Again, you'll find if you start using JTAG, you rapidly end up with a bag of different adapters and connectors for different boards and different pinouts and so on, because pretty much everyone's different. I will say this particular board is tied to 3.3 volts. The chip itself, the 232D, can work at either 5 volts or 3.3 volts. Again, if you're going low voltage than that, maybe, I mean, some of the Intel processors are using GTL plus drivers, so they've need to go down to 1.2 volts. And again, there you need specialized hardware. This won't cut it. Oops, sorry. So in terms of actually using this for doing open source debugging, you're going to need some software. And key to most of these devices is OpenOCD, which is Open on Chip Debug. And this really is sitting at the center of your solution. So coupled with something like an FTDI JTAG adapter, again, there's all sorts of other adapters out there, J-Links and so on, that OpenOCD works with. Just FTDI is kind of very popular at the low end. OpenOCD has also got a shell interface. You can telnet to it by default port 3333, and that will enable you to issue commands much like you do to a ROM monitor, look at registers, read memory, write memory, see what the state of the CPUs are, and so on. For actual debugging, you're going to want a debugger. Normally, really, that's GDB, which is a command line to, debug tool, so coupled with some sort of IDE. So yeah, so OpenOCD provides most of that ROM monitor capability, and it also has TCL scripting available. So if you're trying to do some complex board setups and such things, which sometimes are necessary, that's all possible. In terms of the debugger interface, GDB serial is the interface that's used. And again, you can look in the, if you're interested in that side of things, the GDB info pages have got loads of, well, I say loads of information. They document the protocol. And although it's called GDB serial, normally that's then run over a TCP socket rather than a serial port. But again, you're still talking at sort of low level in that it's sort of setting breakpoints by memory address rather than symbolic information. And you've got no knowledge of what the application's actually doing or what program's running. It's just very sort of low-level commands. And OpenOCD itself is going to need some configuration. You're going to need to tell it how to connect to the JTAG interface you're using, potentially what type of JTAG interface it is, potentially even what the pins are, how the pins are assigned on your interface. Sometimes, voltage levels or JTAG, but not necessarily JTAG protocol. There's alternatives like CJTAG and single wire debug, which again, a lot of the adapters support. If you're lucky, something that your IDE again will have some information about or will set up automatically based on existing boards. So for the IDE side of things, today I'm going to very soon switch to demo mode, and I'll be using Visual Studio Code with Platform IO. Again, basically you start with Visual Studio, and then all the extensions are there for you to download. Once you start building a project for a specific board or architecture, it downloads for you the compilers and even OpenOCD and various other bits and pieces that you need, the Arduino frameworks and so on. So I found that a good place to start. I will say that I don't consider myself a platform IO expert. For the project I'll show you a little bit later, for just an example, it's a lighting controller, DMX sort of theatre lighting controller, which I put together for the Christmas presentation local hall a couple of years ago, just for Christmas 2019. And I haven't really touched it, Platform IO, or the application very much since. In fact, it hasn't even had the usage I hoped because of COVID. But although I've used a lot of JTAG, this is really at the sort of low end. My usage is more really around the sort of proprietary large-scale projects, again, typically with a safety and security element to them. And their corporations are prepared to pay big dollars. They're not interested in, saving a few £100 by buying a $10 device off Banggood or whatever. They'd much rather have something which works easily and reliably and has got all the features that they need. Again, as an alternative, if you don't like Visual Studio Code, Eclipse, there's a whole load of sort of Eclipse-derived variants, mostly sort of pushed out by the chip manufacturers, so ST is SVC Studio, XP is MCU Expressor, and so on and so on. Again, it's possibly a little bit of a religious thing. Do you prefer Visual Studio or do you prefer Eclipse? And there's plenty of others that may or may not use OpenOCD, like Code Composer, Atmel Studio, and so on. Again, I'm more used to, in fact, JTAG probes in the thousands, which are doing trace and so on. But these sort of low-level devices at a basic level do provide almost exactly the same capabilities. It's only when you start to use the advanced features you notice a difference. So finally, before I move on to the demo bit of this, I want to talk a little bit about the hardware that I was using. So I said, maybe this was a sort of DMX theatre lighting project. So I found this SparkFun board, which has got this feather interface that they use. I see it in the chat. There's some comment about VS Studio Code. It's available for Linux and for OS X as well as Windows. So it's truly cross-platform. You're not tied to just using Windows. Again, I'll mention a couple of little things about that in the demo session. So this device has got a single DMX bus. You've got some opto isolators, which are part of the requirement for the DMX standard. You've got the line driver for the effectively a 485 multi-drop serial interface, and then a whole load of connectors which I wasn't using, which are basically for driving things like your LED strips. There's a shared clock between each of the 3 channels and a single data pin, and then each also has ground and 5 volts. I wasn't using that part of this device. So sitting on that is one of these ESP32 feathers, like I think Tony was using for his project. And in this case, I was using this Hussar 32 debug board, which designed by a top local, Brian Luff. He's got a Tindy site, although it's currently offline. But he does all sorts of funky electronic projects and so on. He should probably be on this group as well. So my JTAG adapter is this CJMCU 4232. So this has actually got 4 channels, although only channel A and channel B do JTAG. The other channels will do ordinary serial ports as well. If I was starting again, I would do this slightly differently. I would instead have one of the new S2 feathers, which effectively it's an update to the ESP32 device with lots of bug fixes and a few new features like the USB controller and such things as well that the old one didn't. But crucially, it's got, I don't know if you can see there, it's got a little JTAG header, which is actually compatible with the ARM style headers. So you could solder in your 1.27mm pitch header and plug this JTAG adapter straight onto it, and you wouldn't need a third-party board in the middle. So with that, I'm going to move over to demo mode. So first, I'm just going to bring up a command line interface. Let me see if I can increase the font size on that. Right, so first thing I want to show you is some of the gotchas I had with OpenOCD. So I was using a board which didn't have a standard script for the interface. So I had to develop my own based on what was already there. So my board is, or my script is called CJ-MCU4232B because I was using the B interface for this board. And essentially, it needs to be told what type of interface it is and the USB vendor code and device code. So that's how it identifies it. I need to tell it which channel it's using, 0 or 1. To give it some information about how the pins are configured. So the normal JTAG pins, the normal 4, are in the low bits or in the low nibble here, and that was entirely standard. I've used this JTAG interface with a couple of other boards which needed the test reset and system reset as well, so those are on a couple of other pins. Again, that's relatively standard for these FTDI devices. The main thing that was different for this device is really just this number here, which says it's the 4232. Then I also had to put a configuration script in for the board as well. So again, most of this was derived from an existing file, but it was just to do things like set my reset configuration to say we're using or don't try and drive the soft reset or system reset and the test reset pins because they're not in use on this board. And in fact, if you do drive the reset pins and they're connected, then effectively that's connected to the enable pin on the board, so your board powers down and things. It just creates a pain. I've just limited the adapter speed down a little bit on this board because I'm using a rather hokey adapter as well. So when I tried to start OpenOCD from the command line the first time, I got a curious problem on Windows, which I hadn't seen when I tried this on Linux. Originally, I did this entire project on a Linux machine, but I since sort of changed the laptop to be running Windows. And the key here is it's unable to open my device. And eventually I discovered that the problem there is the USB libraries that are used by FTDI for Windows require you to, libUSB, require you to change from the FTDI driver, which is the default for the serial adapters, to the WinUSB driver. So this USB driver tool I got from the Visual GDB website. And then when I try again, this time it connects correctly. And I can see my ESP32 CPUs. So before I go into platform I/O, I just want to show the start putty and show a few things that we can do with the OpenOCD command line. So now this terminal's not going to do anything useful. It's not responding to commands. If I type the same thing here, it's going to come out in both places. So if I want to, for example, look at my program counter, I can do read PC. If I want to read some memory, I can say memory read word from, let's read from some instructions. Oops, I need to hold CPU first. And then DW, NDR. So M, memory, read, word. There we go. See, I do actually know. Sorry, I know why this isn't working. I've loaded a crashy version of my program to show what happens when we're debugging, and at the moment that means I can't do this from OpenOCD. But suffice to say, there's a command line. You can do some very low-level functions against the JTAG interface to control your board and have a look at what's going on, or control the CPUs. So I'm going to close my OpenOCD session there, because when I start Visual Studio, it will have the ability to it will have the ability to let me start its own copy of OpenOCD. So the configuration for JTAG is part of your platform io.ini file. So the key bits here to make it work on JTAG is I have to set a debug tool. And here again, I've set my tool to match that config file which I was using. Now there's some magic there too, in that I had to go to So among my supported debug tools, when you add a new device or a new JTAG interface, you need to add these to your supported debug tools line in the platform.py file. Again, it wasn't exactly documented anywhere. I had to just find that for myself. So back to Visual Studio Code. So that's where my debug tool is set. I set my OpenOCD board. This matches my config file, which I created for this board. I can override the debug speed here as well. So my little example, so I pulled together from a few bits. I've got an ArtNet Wi-Fi library, which enables me to talk to the board over the built-in Wi-Fi interface on the ESP32. I've got a DMX library, which enables me to talk DMX on one of my serial ports. And then I've got my main code, which basically controls the whole thing in typical Arduino style, where you've got a setup function and a loop function. My loop function is basically just reading from the ArtNet and processing it. So when I try and run this, now I can press F5 and that will create me a debug connection by my OpenOCD and start trying to download to the board. You can see it's going to program Flash, and eventually it will finish. It won't take too long, 2 milliseconds, and it will start running the program and stop at the entry point in main. There we go. So this is the Arduino app main entry point. And I've got some breakpoints set up from before. I can add breakpoints by clicking on my break dots. If I then run, it'll run and hit presumably this breakpoint. My breakpoint somewhere else. There you go. And if I run again, I'll hit one of the breakpoints I've set in my program, I think. Yeah, so I've got a breakpoint there just before we write a DMX test packet. And if I look at this test packet, this is what you're supposed to send on the DMX bus until you've got some valid data, and it should all just be use. If I expand it, capital U's. So, well, it's just fetching that data. DMX enables you to control 512 channels. So effectively using packets of 513 bytes. The first byte is a control byte, and all the rest are just a different byte potentially for each channel. You know, an 8-bit value to say how bright you want a light to be, or to move to a particular rotation if you've got a moving head device, and so on. Or maybe to select a different filter. So if I, again, hit F5 and let this continue running, it's hit my startup code, so I'm going to be just writing some stuff out on the serial port. And before I know it, I've got a problem. It will have hit an exception, so it's taking a long time. So I've got the data view on. Because we hit a trap. Let's have a look. I bounced on the F5 button. So actually I've covered it. Let me just get rid of a couple of these breakpoints so I can get back quicker and restart the program again. Because this is really, what I'm about to show is one of the really nice things of JTAG, is that oftentimes you can set things up so you trap errors, which otherwise would be really difficult to debug, and you wouldn't, you get into a position where it doesn't work. Why doesn't it work? Well, I don't know what it's doing. I can't see it. I've lost control of it. So in this particular case, what we've got is there we go. We've got pause, but because we hit an exception. And this is where I bounced on it before. So the first time we hit the problem, we've now got the ability to debug this. So I can look at my call stack for this task which is in error, and I recognize this. But most of this stuff is OS stuff. This is my first function that we've got. So if I click on that, what I can see is, well, I've got a comment which says I'm doing something stupid. So that's a good clue. But what I've done is I've deliberately taken or dereferenced something which I shouldn't have dereferenced, and used that as a effectively the size that I'm mem copying. So I'm copying far more data than I should be, and written over something where I don't have access. Well, effectively caused a problem. And the nice thing about JTAG is it's taken me right to the source of the problem. In this case, because I tracked that as an exception, and I didn't have to do lots of hunting around, lots of guesswork, lots of code reading, trying to work out why it doesn't work. I'm there pretty much at the line where the problem happened. Now, just for completeness sake, I'm going to comment out the wrong one and correct it, and then we'll run this again. And I'll be able to show you that this system does actually work. Sorry, I need to stop debugging and rebuild and download again. It's still really running, which is okay. Let's let it go. I'm going to get rid of that breakpoint as well, because right, so what I'm going to do now is attach to the access point which this ESP32 is providing, which is on the other screen. And then I can start my console here, which is my Lighting console. If I just top of those. So now I've got packets arriving, and I can go to my desk. And if I start turning up the lights, or in fact, if I'll just change camera so you can see what's happening. So if I turn up the lights, sorry about the flickering, but you can see I'm actually in control of this little lamp that I've got pointing at the board.
You didn't change camera.
Oh, is that not gone? The desktop still, if you look at my video, the video of me, it's probably got the board. Can anyone see it or not?
We still see the.
Right.
Yeah, it's on the other camera. Yeah.
You can see it or you can't see it.
We can see.
Good. Yeah, so I can change. It's a multicolor lamp, so I can change what colors are going on. So it's flickering, but that's LEDs for you. There we go. Some flash, some strobing as well. So that's my little setup. As I said, it was a little bit of a hokey display, a hokey JTAG connection. I've got just 5 little wires connected back to my CJ MCU board. It's not the most elegant of solutions, but it does work. I'll stop that strobing because it's putting me off now.
I don't know where they say they can see the other camera, but I just see your desktop with the IDE and your QLite Controller Plus window.
Yeah. The thing which would normally show my face while I was talking should be there. If I stop sharing, actually, that may do it. Can you see it now?
Yeah, I can see it now. I could see it before, but I can see it now on the main screen.
Okay.
Yeah, strange. I couldn't see that anywhere.
I don't know why. That should have replaced my ugly mug at some point, but
on the view of all the people who are in the session, and you can change it to just the active speaker. So there's one screen where you can see the screen share, and there's another screen with the chat and another screen where you can show all the active speakers. And it was on there.
Oh, okay. So really that's the end of what I wanted to show you this evening and give you an idea of what's going on. And if you've got any questions or need more information, a bit of a whistle-stop tour, really.
Julian, so is SWD a subset of JTAG?
Well, not really. I mean, JTAG isn't well defined in terms of the commands that you're issuing to a particular processor to get it to do things. It's really much more about that synchronous serial interface and clocking in instructions. The instructions you clock in and what the data means that goes with those instructions is entirely at the behest of the chip manufacturers. And so Espressif with its ESP32 will be doing completely different things to ARM with and different things to power. So, you know, even things like about the only instruction which is standardized is the bypass instruction, which is used for effectively telling the device to ignore commands. It basically puts a 1-bit data register in the data scan chain. But most of that's hidden for you by OpenOCD. If OpenOCD supports a particular device, then mostly you don't have to worry about what JTAG itself is actually doing.
Right, okay.
Yeah, I've seen lots of JTAG connectors on lots of devices, but I just thought it was a serial interface of some kind. So thanks for that.
It is a serial interface of some kind.
But a little bit more.
It is, yeah. As I say, you're never going to connect to it with a terminal.
So when you're starting a new project or a new device, do you always like set up the JTAG interface first, or do you only do that after you run into troubles? So what's your process? Just wonder if it's something you use all the time or whether it's just sort of a special case thing.
As soon as I start trying to make it work, then I'm using JTAG. I'm probably using a debugger before I'm using JTAG though. So as I said, I actually work for a company which sells one of these sort of multi-thousand-pound sort of debuggers and compiler suites and everything else, again, especially to the safety sort of market. And there you spend a lot more time being diligent about the design and working out exactly what you want the system to do before you even start writing code. But at the point where you've got something that builds, at that point, I normally start poking around in the debugger, you know, because that helps you understand the code. What's referencing this value? You know, what does the call graph look like? These sorts of things you can generate statically. Again, mostly from a support perspective, I get thrown big chunks of code and say this doesn't work, and I start. You know, JTAG gives you some clues as soon as you try to run it, but oftentimes it's a bit of detective work back in the debugger. Sort of, okay. In my example, it was I'd made something right beyond the end of its allocated space. I don't know exactly what it did. It probably overwrote something that was critical, but fortunately, there JTAG took me straight to the problem. But again, you still got to understand this doesn't work, but what was it intended to do? Rather than just I can stop it crashing by making this change.
Yeah, I've found it pretty handy to settle turf wars between it's a hardware fault or it's a software fault. So it's a handy tool to find out where it is.
Yeah, I mean, and again, one of our other products is an operating system for safety and security. And so doing things like stepping through interrupt handlers and stepping through context switches and things like that can be really crucial to working out exactly what's going on, especially when that's coupled with trace capability. So there I can run backwards and run forwards through the code. So I can set a breakpoint and say, run backwards, when was the last time this was hit? And then start coming forwards again. Or, the classic, you step over a function and it went wrong in that function, and now you've got to try and get the system back to that state. But with trace, you don't. You've got the state in your memory. So you can go back and then step into or step back into the function that you just broke it with. So, it's a powerful tool. This is at the basic end of the very powerful tool set.
So Julian, in the example where you had the syntax was wrong in that memory copy instruction.
Yeah.
What made
back there.
The codes point to that line? How did the debugger know that was the root cause?
Okay, so what happened was this line caused a processor exception eventually,
okay.
And that was trapped by FreeRTOS, which is running under the water here.
Mm-hmm.
So it got an exception, and and the debugger was smart enough to know that that exception was associated with this task. And so looking at the call stacks, I could relatively easily look up and say, well, what was my program doing at the point when this crashed? Which, because I deliberately put the bug in there, it's kind of a trivial one, but it was obvious that it was my silliness. If it was something going wrong in FreeRTOS, then I'd have to install the sources for FreeRTOS and start poking around in what it's doing. But this was a sort of a simple example, so relatively easy for me to sort out.
Yeah, I understand. Okay. Thanks.
Cool. Any other questions, anyone?
Not really a question, but like I did appreciate this. I learned a lot, so okay, I'm appreciative. Thank you.
Yeah, did learn a lot. Very good. Anything else, anyone? Great, thanks very much, Julian. That was really good.
No problem. Thank you all.